So here's another example. I'd call it a discrete probability example where we can count things, just count them up to find the probabilities. We can list the entire sample space. A number is randomly selected from the integers 1 through 15, so I could write all 15 of those or visualize all 15 of those. What's the probability that if we randomly select a number that it's part A divisible by 5? Well, we just have to count up how many of those 15 are divisible by 5. Well, there's 5, 10, and 15. So there's 3 of them. So the probability that the number we randomly select is divisible by 5 would be 3 out of 15. Or you could reduce it to 1/5 or write it as 0.2. Okay, all of those numbers would be equivalent to each other, or 20%. Make sure when you're doing the online homework that you answer in the format it asks for so that it counts it correctly. If it asks for a percent and you tell it 1/5, it would count it wrong because you would need to give 20%. But in general, any of those answers would be equivalent mathematically. Part B, what's the probability that it's even and divisible by 5? And then on part C, we'll do or. We're going to get some rules eventually for the probability of A and B, probability of A or B, of combining events together, because when the sample space gets more complicated, we're going to want some rules we can apply. But right now, we can just count things. So what's the probability we pick a number that's even and divisible by 5? So we'd have to have both of those properties. Well, there's only one. Okay, to be divisible by 5, it could be 5, 10, or 15, but 5 and 15 are odd. The only one that's even is 10, so it's only 1 out of 15. And then part C, if we change to an or, there's a lot more possibilities. So if it's even or divisible by 5 or both, we call it the inclusive or. It could be even or divisible by 5 or both. It would be a success. So if we count those up, I think my animation's off on this one, but if we count those up, we're going to wind up with 9 out of 15. There's 3 of them that are divisible by 5 that we've seen before, and if we throw in the evens, and we don't want to double count the 10 there, we just want to count each number that's either even or divisible by 5, you wind up with 9 of them. Okay, and then some rules here, the two extremes. Your probability, you can write it as a decimal. It's always going to be a number between 0 and 1. You can also think of it as a percent. It's between 0% and 100%. And the two extremes there, if your probability of an event is 100%, there's a 100% chance it's going to occur. So if your probability is 1 or 100%, the event is certain to occur. Or if the event is certain to occur, the probability will be 1. And then the opposite of that, if there's no way it can occur, if the event's impossible, its probability would be 0. We're going to throw that into 1 on this example here. So suppose that a coin is tossed 3 times. Construct a sample space for this and then find the probability of getting different numbers of heads here. So you can just kind of brute force do this. I've got a little bit of a pattern of how I did it. There winds up being 8 possibilities. Okay? I kind of thought of it as, well, let's let the first toss be a head and then see what happens, and then the first toss be a tail. If the first toss is a head, the second one could be a head or a tail, then the third one could be a head or a tail, and you just list them all and you wind up with 8 possibilities. It could be that the first, second, and third are all heads. You have the first one's a head, second one's a head, third one's a tail, and so forth, and you see the sample space there. Okay. And then we can just count to find the probabilities. So part B, find the probability of obtaining 1 head. Okay. So there's, I think, 3 of these, right? The head could be on the first, the second, or the third toss, and the others be tails. So you have head, tail, 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 head, tail, or tail, tail, head. So the probability that we get exactly 1 head would be 3 out of 8. The probability that we obtain 3 heads, well, there's only one way for that. All 3 tosses would have to be a head, so that's 1 out of 8. And then what about D? What's the probability of obtaining 4 heads? Think back to my previous slide, right? There's no way to toss a coin 3 times and get 4 heads, so it's not a trick question. It's just pointing out that we understand if it cannot happen, the probability is 0. Okay? Let me also show you a lot of these discrete examples. I've built simulations with GeoGebra. So here's my little applet that I built with GeoGebra where I can simulate tossing 3 coins or tossing 1 coin 3 times, whichever way you want to think about it. And I can do it one at a time, and it'll count the number of heads that occur. I've got a table where I'm counting the number of instances where there's 0 heads, 1 head, 2 head, or 3 heads, and I could do it a large number of times. We found that the probability of getting 1 head was 1/8, which is 0.125. That's the theoretical probability, which means if I were to do it, theoretically an infinite number of times, then 1/8 of the time of those infinitely many would come out to be 3 heads, so in a very long series of trials. When you actually do it a large number of times, we call that the empirical probability. So I wouldn't expect to get exactly 1/8, but if I do it a very large number of times, like let's say 10,000, I would expect to get something very close to 1/8 for 3 heads. And with 10,000 on this particular simulation, I got 0.1354. So 1/8 is 0.125. So I'm off in the hundreds place. Let me do it again. Okay. That time, and I did 10,000 trials again and counted the numbers much closer. I got 0.1227. So the more times I do it, the closer it's appearing to 1/8. So that's your theoretical probability and your empirical probability are going to get close together when you do it a very large number of times. There's 100,000 trials done instantly with my computer that can do them so quickly. And we got 0.1244 for our empirical probability of 3 heads, whereas the theoretical probability is 0.125, so extremely close. Probability of getting 1 head was 3/8. I'm typing in my calculator here just to add 0.375, 0.375, and we got 0.377, 0.3738. So the probability of 1 head, 0.3738, whereas the theoretical probability is 0.375, so also extremely close. So we can simulate things, and we'll see what's called the empirical probability, which is where you actually do it a large number of times and see what happens. But by counting and thinking about the sample space and what could happen, we get what's called the theoretical probability.